Hi, I'm Ben, and I'm the research coordinator.
I'm Danny, I'm team leader.
I'm Alex, I'm the physics expert.
I'm Alberto and I'm the technical expert. Today we're going to talk about collisions, but before that we have to know what a collision is. So the common use of the word collision, it is used to refer to an accident when two or more objects crash. But scientifically speaking, a collision is an event in which two or more bodies exert forces on each other by a relatively short time.
There are three types of collisions: elastic, perfectly inelastic, and inelastic.
Alright, so an elastic collision is a collision where momentum and kinetic energy are both conserved. And what that looks like is, so say this car right here is at rest, and this car is coming at it, and these are the same weight. This one's gonna come. Alright, this one's gonna come, and this one's gonna stay at rest or bounce off. If this one's lighter, let me take one of the weights out, or both of the weights out. This one's gonna bounce off this one, and this one's gonna move. See, this one goes backwards, and this one goes forwards. And what an equation of that looks like, and there's the equations you use for those. First you use this one, which is conservation of momentum, and then once you find this and do this equation, you come down and use one of these equations for conservation of kinetic energy. And I'm going to do an example problem.
Sweet.
So an example problem of elastic energy would be something like this. A 25-gram object traveling to the right at 20 centimeters per second collides elastically with a 25-gram object moving in the opposite direction at 15 centimeters per second. Find the velocity of each object after the collision. So first we're going to start off by using the conservation of momentum momentum equation, which is m1 v1 plus So we're going to use this equation to start out with, and what we have is 25 grams multiplied by 20 centimeters per second plus 25 grams times negative 15 centimeters per second equals 25 grams times V1 plus 25 grams times V2. So what we're trying to find is the final velocities of each of the objects after they collide. So this comes out to 500, 25 times 20 is 500. Minus 375 equals and then 500 minus 375 will come out to equal 125. So 125. So you see all that. 125, not 1,000. Alright, so then we're gonna have to use the this equation right here. The V1 minus V2 equals V2 minus V1 final. And I'm gonna erase some of this right here, so get one last good look at it. So V1 minus V2 was V2 F. Okay. So what we have is 20 centimeters second minus V1. So 20 centimeters per second minus negative 15 centimeters per second equals V1 or V2 minus V1. And so that comes out to 35 centimeters per second equals V2 minus V1. And you can bring over the V1 to eliminate the negative. So plus V1. And these will cancel out. So V1 plus 35 centimeters per second equals V2. And so now that you have V2, you can plug it back into a different equation. So equals 20 centimeters per second. And now we just gotta plug that back in to find V1, so I'm gonna erase this. So we got V2 equals 20 centimeters per second. So I'm gonna erase this. And so 125 centimeters per second. So you plug it back into the original equation. Then you can just combine like terms. And equals. And there's your final answer.
Perfectly inelastic is one in which the maximum amount of connecting energy has been lost during the collision. And most of the time you can tell the perfectly inelastic when two objects stick together and like tackle in American football. It will be like this. E- 18.3 kg car traveling at 7.25 meters per second has head-on perfectly inelastic collision with a 2 kg car traveling at 1.69 meters per second. What is the velocity of the joint car? So we already know M1 equal 18.3 kg, M2 equal 2 kg, V1 initial equal 7.25 ms. V2 initial equal 1.69 meter per second. And we are finding VF. So we're using M1 times V1 initial plus M2 times V2 initial equal M1 plus M2 VF. So VF equal 18.3 kg times 7.25 meter per second plus 2 kg times 1.69 meter per second. Divide by 18.3 kg plus 2 kg. It will be 136.055 kg meter per second divided by 20.3 kilograms. And it will be 6.7 meter per second. That's the final answer. Thank you.
An inelastic collision is when two objects collide and momentum is conserved. So when this car hits this one, they're both going to move in the same direction. This one's just going to move a little bit slower. So it's like that. This one's still moving. So an example of an inelastic problem would be a 0.30 kilogram hockey stick traveling at 50 meters per second collides with a 0.80 kilogram hockey puck at rest. After the collision, the stick travels at 25 meters per second in the same direction. What is the speed of the shot? So the equation for an inelastic collision is mass 1 times velocity 1 plus mass 2 times velocity 2 initial equals mass 1 times velocity 1 plus mass 2 times velocity 2 final. So the mass of the hockey stick is 0.30 kilograms times the velocity when it's starting, which is 50 meters per second. And the mass of the hockey puck is 0.80 kilograms. And since the puck isn't moving, it's 0 meters per second. And the final mass of the hockey stick is the same as it started, so it's 0.30 kilograms. And after it collides with the hockey puck, it's going 25 meters per second. And the hockey puck's mass is still the same, so it's 0.80 kilograms. And we don't know how fast it's going after it collides, which is what we're trying to figure out. So these two times each other is 15 kilograms meters per second plus 0 equals 7.5 kilograms meters per second times 0.80 kilograms V2. That's V plus. So we had minus 7.5 kilograms meters per second from both sides. And on this side you would get 7.5. On this side you'd get 80 kilograms V2. You'd divide by 0.80 kilograms. And you would get 9.375 meters per second as the speed of the shot after the collision. A real life example of a collision was when the Titanic hit an iceberg, and a way of seeing that is finding the force that the Titanic hit the iceberg with. And the equation for force is mass times acceleration, and then acceleration is change in velocity over change in time. And the Titanic was going 24 miles an hour, but for this equation you need to use velocity, which is meters per second. So 1 mile an hour is 0.44704 meters per second. So you have to use a conversion factor. So it would be 1 mile an hour over 0.44704 meters per second times velocity over 24 miles an hour. So your velocity would come out to equal 10.72896 meters per second. You have to do the same thing with tons because you need to get it to be mass, and it's 46,000 tons. So for that one, you would do 1 ton over 907,185 grams, because that's how much a ton is. Times mass over 46,000 tons. So your mass would come out to equal 4.17305 times 10 to the 10th. So then you would take those numbers and plug them into this equation to get the acceleration. So your acceleration is your change in velocity. So it's 10.72896 minus 0 because it was going 0 when it hit. So it would just be 10.72896 meters per second. And then over the time, and it was in contact with the iceberg for 7 seconds. So that'll be over 7 seconds. So that would equal 1.533 meters per second squared. And then you would take the acceleration and plug it into the force equals mass times acceleration. So force equals 4.17305 times 10 to the 10th times acceleration, which we found was 1.533 meters per second squared. And when you do that out, your force equals 6.3973 times 10 to the 10th newtons, and that's how much force that it hit the iceberg with.